to introduce Chris Ray from Stanford University. He received his PhD at University of Washington. He has received a ton of amazing awards, including the SACOM Dissertation Award, the NSF Career, the Sloan Award, and he's a certified MacArthur Genius. So he has also won best papers in different communities in POD, SIGMOD, and ICML in different across different scientific communities. And he has co-founded a company, Lattice.io, that was acquired by Apple. And he's also involved in several other companies. Research from his group has been incorporated into several scientific and humanitarian efforts, such as the fight against human trafficking, along as many other products that are used in technology today. He's a very exciting speaker, and I'm eager to hear what he has to say today. So Chris, you have the floor.
Thanks so much. Yeah, so thank you so much, Alex, for the introduction. It's really exciting to be here. You know, this is a nascent community in MLSys, and I'm really excited to see, you know, it growing and so many exciting different folks and so many exciting papers. So real pleasure to talk to you today. What I'm going to describe in this talk is some of the work we've been doing in my group in kind of two phases. So the first part, I'm going to talk about this work we've been doing in weak supervision. And it's an area that's just kind of growing up. So I'm going to share with you a bunch of examples where it's getting used, and it's growing pretty quickly. In the second part of the talk, I'm going to describe some theoretical nuggets. You know, there'll be a little bit of math, not too much, but to describe kind of what's going on in this area of weak supervision, and that you can make some, you know, rigorous statistical progress here. And then in the last part of the talk, I'll describe some things that are worrying me, some things that are keeping me up at night that are about kind of our future directions. Some places where this new breed of systems that I'll describe seems to be going a little bit askew, and it's a place where I hope more smart folks in this room jump in and solve these problems, because I'm very interested in just finding those solutions. So there's this phrase which is kind of irritating. All my graduate students hate it, software 2.0. One of them actually insisted that as a condition of a grant when he became a professor, he no longer had to use that phrase. But I still use it, as irritating as it is, because I think it captures that there's something really interesting going on with how we're building software. So when you think of machine learning, you traditionally think of a couple of different kinds of projects, things like translation, medical imaging, robotics, things like that. And one of the things that's gone on inside these systems that's really interesting is that they were constructed in kind of classical machine learning ways a couple of years ago, but they were very expensive. So for example, Google had this translation system that they built that they talked about. And in 2017, they changed their system from being 500,000 lines of traditional C++ code to being about 500 lines of data flow code, sort of TensorFlow code. That wasn't the whole system. It was kind of those hardest bits, those heuristics you really had to work hard on. Those were encapsulated in this machine learning. But it's not limited to that. It's actually, you know, a whole host of different places. People are starting to use these ideas of taking where they find heuristics that are hard or difficult to maintain, and they're replacing them by machine learning. And that's what we really mean by this idea and behind software 2.0. Now, why is this happening? At a very high level, you know, people focus on quality in machine learning all the time. I focus on quality in my research papers. But really, in my time in industry, I realized that a couple of things were really important in driving the adoption of this new wave of machine learning techniques. One is that people simply can build products faster. The teams that use machine learning versus the teams that don't use machine learning in these new ways, the difference is night and day in how quickly they can ship. Another one that's very underappreciated is that actually machine learning, because it has this nice data flow code underneath the covers, actually it's very easy to ship to the data center. So when you build a big and large system, you know, of moderate size even, you have to worry that when you put your tool out there in the wild, it's not going to blow up memory, it's not going to blow up your runtime budget. But because you have these nice kind of data flow underneath the covers, you can have much, much more reliable runtimes. And so these teams can ship dramatically faster. Teams are shipping, you know, weekly. Facebook retrains their embeddings daily. There's a lot of ways that you can get fresher and more interesting data into these systems. And they've sort of become, you know, this new JVM, which I think is really underexploited by a lot of the systems research. There's also really huge implications to hardware with Kunle, who's there, Ola Kutten, the author of Multicore. We founded a company called Samba Nova that's exploiting this, and there are many companies in this space trying to understand how this impacts the next generation of applications that you're going to build. The last bit is an issue about maintenance, and I'll just put this out there as a large high-level piece. Basically, a lot of the code that was written previously for these machine learning systems had to have a ninja behind it, someone who is trusted to manipulate all those little features. But what we've seen is that over time, you can de-skill these systems and make them dramatically easier and more resilient to teams changing. And so what I'm trying to get across to you is that, to me, some of the most exciting stuff that's going on in machine learning is actually at this intersection of what happens with software engineering and how do teams change. I use this phrase, software 2.0. Right. So what I want to look at is a little bit more technical than that high-level vision. So what do machine learning applications really consist of today? So they have really three parts. They have a model, they have some data, and they have some hardware. Now, state-of-the-art hardware, you can get in a variety of different places. What's more interesting and perhaps less well recognized outside of machine learning is that actually state-of-the-art models are something that you can obtain pretty easily for most of the things that you care about. Things like Hugging Face allow you to pip install really state-of-the-art natural language processing models in a way you couldn't imagine even a couple of years ago. And moreover, these great tools that the large companies have put out mean that when someone's starting from a problem, they're starting from a much, much higher bar. But there's still one challenge, and this is going to be our focus today, which is on this training data piece in the middle. Now, in some ways, training data can't be commoditized, right? It is in a very real sense the way you describe what your problem is about. It's how you program your application in this new style of machine learning. So in some way, if that were to commoditize, so would your application. Now, when we think about it, we started to look at this, we started to wonder, why is training data something that is like this massive bottleneck, but yet we apply very few tools from computer science to the problem of training set data construction, maintenance, management, all those good things. Now, when I first started talking about this in 2016, people reacted kind of like this. They say, well, no, supervision is not something you get to mess with as a machine learning person. It comes directly from God herself. When I teach machine learning, the first day we say there's some XY pairs. Where did they come from? I don't know. I don't tell you. They just showed up, and then we start machine learning. Okay? But this seems kind of wrong, right? Anyone who's actually built any of these systems knows that our life isn't like hanging out with Beyonce. It's more like living in the sewers, right? We're basically faced with a bunch of dirty, messy streams of data that we have to merge and create to be able to build kind of an interesting pipeline. And that's actually where a lot of our effort is going. So when I said this, people say, oh, well, that's just an engineering problem. Well, most of computer science is an engineering problem. But could we potentially build kind of a mathematical and a system structure to really deeply understand what's going on here and maybe just make it a little bit less awful, okay? So a lot of the ideas I'm going to describe to you, I'm not claiming they're the best way to do absolutely anything. I'm just saying they're a little bit less awful than what was there before. And weirdly enough, people are willing to use things that are a little bit less awful. And I'll show you in the second part, you can prove fun theorems about these things. It's a little bit more like the Wild West of what you can actually show. But it's exciting to watch even some of the folks in this room start to pile into this new theoretical area. All right. I'm going to go one step beyond that for a little minute and say to you that actually supervision may be where the action is. All that action is in the sewer. And actually, if you look at where people are putting out press releases now, 3-4 years ago, they were always about the new model that they were putting out. Transformer was a big deal when it came out. But if you look now, where most of the web companies are putting out their exciting things, they're actually tricks about how you do augmentation and how you do supervision. And that's been a pretty massive change in where machine learning is headed. So what I'll claim is that modeling differences are vastly overrated, and supervision differences are vastly underrated. And what I mean by this is not to say that one's better or worse than the other. I just mean in terms of intellectual bandwidth, we spend a lot of time on modeling in the traditional sense, but less sense in trying to really understand what the heck is going on in supervision. And I think that's something that we can spend a little bit of effort on. So I like to build applications. I like to build things in industry, but also these are things that you can collaborate on any university campus with. So let me tell you a little story that'll kind of run throughout the talk about some work we did with radiologists. The way you can identify the physicians is they're the people in ties. Anyone in a tie is a physician. Anyone not in a tie is not a physician. Okay? This is work that we put into radiology, which is the flagship journal for this clinical area, and that will become important in a second, in January of this past year. So almost a year ago it appeared. Okay? And it was important that it's clinical because we want to understand, are we doing the right things here? So what's the problem we looked at? We looked at this problem called triage. So basically you have pictures of radiographs. And it turns out that oftentimes there's not an expert around to actually look at the radiographs. And we're not saying this has been something that people write lots of articles and the nerd tabloids about. Right? Now, what we want to do is we want to just scan through all those images and just highlight, hey, physician, take a look over here. This is worth your time. Okay? We're not trying to replace anybody. We're just trying to augment them and figure out what's going on. This seems like an ideal place for machine learning. People aren't even looking at the data. Maybe we could find something useful or interesting in there if we do a good enough job. So one of my students, Jared, postdocs Jared, a couple years back decided, hey, what I'm gonna do is I'm gonna actually try and solve this for real in a clinically meaningful way. And we looked at this and said, this is a perfect problem for deep learning on the kind of clinical side. Let's go out there and build it. Well, it turned out that even understanding if that was possible was actually a pretty hard challenge. Turns out there was no benchmark data set. Actually, some of those folks in ties just put one out just a couple of months ago. The effects of data quality at the time were totally unclear. That'll be important later. There was no assessment of existing algorithms. There were people publishing new algorithms on these things, but there was nothing that said, how well do the existing problems do on this triage task? And there was no feedback, importantly, from the clinical community. And when I come to the end of the talk about things that are worrying me, you'll see that that lack of feedback from the clinical community can sometimes lead to some pretty perverse outcomes. So Jared spent a year of his life basically going around to clinicians and getting them to label. It wasn't glamorous work, but it was important work, I think. And he went and he had them actually look through labels and figure out what they're actually meant by various diagnoses. And he created a rich set. He studied all the ways that sort of artifacts crept into the data and all the rest. Published it in a clinical journal and got a bunch of feedback. Very, very proud of him. Okay. What's important for our discussion is one thing that came out of this. After you clean up the data, you get a chart that looks something like this. I'm being a little bit glib here and selecting one out. Take a look at the paper for more details. At the bottom there is a model called DenseNet from Killian Weinberger at Cornell. Amazing model, won CVPR best paper, one of my favorites. And you see it does get the highest accuracy of any of these different methods. That model that's at the top is this bag of words model, bag of visual features model. This is something you could have trained kind of comfortably in the late 90s. Okay. Sure. Okay. All right. So as we look through these models, the thing to take away is that something that we could have trained comfortably in the 90s versus something that's really state of the art right now had only a couple of points in difference. And that's pretty interesting in this application. Okay? It turned out actually that what was the key difference, and I'll come back to this a couple times, had to do with label quantity and label quality. And it was much more important than, as we'll see, this model choice. And so throughout the talk, I'll kind of use 2 to 3 points as being something that means, hey, that's a significant thing that we should look at. Okay. All right, so you may look at that, and I've given a talk, at ICML about this, and kind of folks said, well, maybe that matters for those, simple learning problems in kind of that space over there in medicine, but it doesn't matter for the problems we care about on benchmarks. I would say that's not actually accurate. It turns out in problems like, even CFAR 100, if you take out augmentation, which is a data preparation technique, it turns out that you drop by almost 13 points on average across almost all the models. Okay? It's a huge amount when in fact people are fighting over tenths of points that are in here. Turns out, as I mentioned, actually training data signal is actually key to pushing the state of the art. So there's a line of work, in part started by 2 of my students, Alex and Henry, who had this idea. They said, look, what we're going to do is people are doing augmentations. What if we just said, here are the set of augmentations you have access to. We'll learn how often to apply them and in which order. Okay? What they call augmentation policies in a 2017 paper. Google picked this up and did an amazing job with it. They actually showed that they could train these really interesting and complex models, and they pushed the state of the art on ImageNet effectively by doing this again and again through a series of great papers. A second class of this model is actually done by a person who's a postdoc in my lab now when she was at Facebook and is now going to be a professor at Wisconsin named Sharon Lee. And basically what she showed is that she could train an image model by taking a huge amount of weakly supervised hashtags and using that to, again, supervise an image model. If you've paid attention to this line of work around does ImageNet generalize to ImageNet from Ludwig Schmidt and Ben Recht and others, you know actually that this was the only model that was above the trend line and robust into a statistically significant margin. So my point is both of the ways that we've actually improved the state of the art, at least relatively recently, have come from this idea of looking at supervision, not looking at model architecture choice. All right, so just a little plug. Sharon wrote up a great blog post. I invite you to send your feedback about automating data augmentation, trying to cover folks' work. So far, people who have emailed us are actually already covered in the blog, which is great. But please send notes if there's things you think we have missed in this kind of 4-part series that she put together. I'll also plug one of my students, Sen, who's here, wrote a great paper very recently where he showed that instead of having to do a more complex reinforcement learning style approach to estimate augmentations, you can actually do a very simple population level approach and get state-of-the-art accuracy. And importantly, have some theory to explain crazy things like mix-up. If you know augmentation, mix-up is a particularly perverse kind of augmentation. You can kind of understand what's going on underneath the covers. What I want to talk about for the remainder, though, is really about data labeling itself. So think about classification problems. And I want to talk about what we can do there because we have a robust statistical theory to deal with it. So when you think about creating training data, I have this idea, that it could be better in some way. So what are things that you don't like about training data? Well, one, it's super slow to collect. It's often the case that in industry you say, oh, I want to collect some training data, and then it's several months later before you actually get that data in any kind of reasonable quality. It can be expensive, and it can be static in ways that I'll unpack in the next slide. Okay? So what do I mean? So as I mentioned, collecting manual labels is slow, both to get them initially, but the problem is humans don't scale in a nice way. Your first label is kind of as expensive as your last label. Okay? And so it's really an expensive process to get to scale. A second issue is that it's expensive. We had a Nature paper this year where we were looking for something that happened, we thought between 0.5 and 1% of the time. That means roughly about 200 videos in this case that a radiologist, an expert, has to look at to make the diagnosis. That's an extremely expensive operation that you have to deal with in these settings. The last bit, and I think systems people recognize this in a way that maybe machine learning folks don't at first. If your first application, you collect sentiment analysis and you say, I want positive and negative, and then someone comes back to you and says, I want positive, negative, and neutral, you're kind of toast. You basically have to go through all of that training data to be able to understand which ones were the neutral and reclassify the whole lot. So now I don't claim I have a solution to all of these problems, but I have something that can do a little bit better in along at least one metric. And let me explain kind of what this idea is. The idea is we're going to bring code kinds of ideas to how we create training data. Okay? And we're going to call it programmatic or weak supervision. Sounds like a crazy idea, and just bear with me for a little while. So what we're going to do is we're going to place labelers by basically little programs that you're going to write, little maps that are going to generate kind of heuristic labels underneath the covers. Those labels are going to be functions. They're going to be pieces of Python code, so they're going to run at kind of AWS speeds and costs rather than running at conventional labeler cost. And they're going to be dynamic in the same way code is, that you can refactor them and relabel them in kind of noisy and interesting ways. The trade-off is that these labels are going to be noisy. And what we're going to have to do is we're going to have to model this noise. They're going to be correlated in different ways. We're going to have to try and understand exactly how they're noisy and exactly how they're correlated, but without using any traditional hand-labeled data. And that's the game that we're going to set first. Right? So the key idea of what we're going to do here is we're going to have an interface to give various different forms of weak supervision. We're then going to have an approach to be able to understand the quality and the correlations of these different sources of information. And then we're going to be able to feed that back into a conventional deep learning model to be able to hopefully get higher quality dramatically faster. And the way that I'm going to assess myself is that I want to get, effectively the quality that you could get as close as you could get if you did that hand-labeled data set, but I want to get it sometimes dramatically faster. We'll see cases where you go from person years down to hours. Okay? That's the kind of thing we're excited about. Now, I want to be clear, we did not invent the idea of using crappy supervision. This goes back at least to the 90s. Marty Hurst had a wonderful paper in the 90s about basically supervising classifiers using pattern recognition techniques. Dan Jarafsky and Mintz had a great paper about doing distance supervision. You have a knowledge base and you use it to kind of heuristically label text. We talked about augmentation, topic models, so on and so forth. The observation we are making here is a little bit one level up. We're making the observation that actually these weak methods were traditionally used in isolated and ad hoc ways. And what we want is a statistical theory that allows us to combine all of these different types. And what that will require is being able to estimate the accuracy and their correlation as well. Okay? And that's what we're going to do. So this is what Snorkel does. It takes in a bunch of sources. This is Project Snorkel, and it replaces these ad hoc ways of doing weak supervision with one framework. And if you can fit in that framework, we'll automate some of the statistical reasoning for you. And what it produces as output are basically a set of labels that are probabilistic. They capture our uncertainty, if you think about a multi-class case, of how valuable each one of those labels actually is. Right? Now, I, of course, am a PI, so I don't really do anything anymore except for like write bad PyTorch code and send. And these are the people who did the real work. Stephen Bach is now at Brown, and Alex will be at Washington, and the rest of those folks just graduated a little while ago at snorkel.org. Okay. Now, let me give you an example of kind of how this would work. So let's say we wanted to label some text as who was a person, who was a hospital. This is a traditional named entity recognition task in NLP, but the idea is totally general, as I'll show you. It applies to video, images, everything. Okay. So the goal is to use labeled training data from weak supervision to figure out how to deal with these three tasks. I'm going to zoom in on a pair of them just to show you what's going on. Okay? So what are some rules that we could write? So we have this text, Bob Jones, blah, 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 leading the cardiology division at St. Francis. So one of our existing classifiers here could run on this piece of text and say, oh, St. Francis, that mention is actually a person. This is actually incorrect. It's a hospital in this case. Another classifier, which actually uses the first classifier, could also vote person. And then maybe we use that distant supervision heuristic that we had before, and we say, oh, St. Francis is actually in our list of hospitals. Let's label this mention as it. And we would hope that this mention, after labeling it, we would learn phrases like cardiology division would indicate that pattern. Even though we don't see it, we should learn that that indicates that what comes next is actually a hospital. Now, the problem, as you can see here, is that the sources that we're seeing, we don't want them to be perfect quality if we want to make them useful. They should be noisy. They're obviously correlated, right? They use the same underlying functions. And we have to figure out how to estimate their accuracies without resorting to traditional hand-labeled data. Okay? So the way this is going to work, we're going to take those labeling functions. We're going to model this as a latent graphical model inference learning problem, which I'll talk about, and how we learn the structure. Then we feed those results to a large deep network. That's going to be our program. And importantly, the key ideas, those probabilistic training labels, are things that record the accuracy. And as a result, there's no hand-labeled data that's needed anywhere in the pipeline. Now, if you have hand-labeled data, go ahead and use it. But theoretically, you don't need it. That's the case we're interested in. Okay? So why might you do this? I'll give you a couple of heuristic ideas. One is that your generalization will actually improve. So people tend to write these rules that are very precise. Okay? But when you have deep models underneath the covers, you can generalize from those precise rules to something that's much more general. And just as the engineer's intuition, this boosts recall quite substantially. So your labeling function may mention certain terms inside of it. We don't get to see those terms, but we learn kind of automatically to generalize this to pick out kind of relaxed phrases of it. You know, a model like BERT underneath the covers, we can leverage that. A second reason is that you scale with unlabeled data. This is something that actually people like quite a bit. As new data arrives, your actual quality gets better as you explore more of the space. That doesn't scale with humans, right? That's data that's generated and coming into you. It's not something you pay to get improved quality. The third one's a little bit more subtle, and we're going to spend some time on why this is important. Let's say that you want to build an image classifier. So you want to look at those radiographs, and you want to actually say abnormal or not. The problem is paying people to look at those images may be very, very expensive. But actually, your organization has a bunch of reports that are laying around that describe what's in those images. What you'd like to do is write some labeling functions over that text and transfer that onto the image. Now, importantly, the image classifier that you're training is available at test time. Well, these documents here are not available at test time. And this allows us to transfer information from offline to online. This difference of servable versus not servable is a big use case that people use for Snorkel. And the reason is the report isn't written when you walk into the doctor's office. You couldn't use it for triage. So being able to use it to train at train time, but not at test time, is a really big deal. Okay? All right. So we talked about these different things here. I hope I unpacked them a little bit. Oops. Now, if I said this, you'd probably think, well, that sounds like a joker idea. What kind of maniac is going to talk about making up training data? Nobody's going to listen to him. And then you would sound a lot like my students. So you were right. But with their good ideas, not my bad ideas, actually it got used at a bunch of places. And I'll unpack some of the places it gets used. This is actually an incomplete set. There are actually a number of folks that are actually using this today. And I'll try and explain why. So one of the places it gets used is at Google. Thank you, Google, for being public about this. They have a system internally they call Snorkel Drybell. And basically what they were doing is using that servable versus non-servable thing that I mentioned. There are some examples in which people are building models, and to get traditional labeled data would take them months or years in kind of these ads kinds of scenario. But instead, by being able to use some of that information they have in various organizational resources, they could transfer that information online using Snorkel and then be able to build their systems dramatically faster. Weirdly enough, because of the collaborations with Google and also Apple, Gmail just recently put out this paper, which is very similar to the Snorkel architecture, and they were very generous when they gave the paper. This is actually how they train their extractor systems that lurk underneath the covers to, extract packages and all the rest of this stuff. They've ported over to these new style of design. So weirdly enough, these kind of weak supervision ideas, which just grew up in the last couple of years, are things that you're probably interacting with, on a sort of hourly time scale if you're like me. So that's pretty cool. Okay. Now, One last bit here, which is from this Apple paper that I'll just show, the amount of weak supervision is in this right-hand column. And the only thing I want you to take away from this is that actually over time, people are starting to build these systems that are dramatically more weak supervision than traditional classical supervision. And that this is actually a reasonable methodology to build a range of different kinds of platforms and applications. All right. So a couple little bits of high-level related work, and then we'll get a little bit more technical. So of course, all this stuff is only enabled because of the great things that the web companies actually put out there. Those large tech companies, JAX, TensorFlow, PyTorch, CoreML. I mean, these things have changed the amount of research you can do. It's like night and day over the last 5 years. They're just really absolutely amazing. The blog post by Andre Karpathy, he got a fair amount of grief when it came out. We were calling our ideas data programming. I sent him a mail almost immediately because it made me realize like a lot of people who were building these things day in and day out realized that something different was going on in how you were actually building these models. So you should check out his original ideas there. One system which I absolutely love is a system called Ludwig. If you haven't checked it out, it's from Uber. Basically, it's a zero-code deep learning system. It looked a little bit like something that, we had some similar ideas when we were doing stuff at Apple, but Piero's system is just really, really elegant in Ludwig. So I would really highly advise that you check these things out. There are all these new kinds of systems that are up-leveling what it means to build machine learning models. And I think it's really, really exciting. Okay. I'll skip through this. These are just citations. This gets used in science. It's not just industry. We have a bunch of, nerd tabloid papers that are out this year. Even from some of these are all from our group, but they're even from other groups in Nature this year that are using our stuff for a bunch of interesting tasks. So it's kind of cool and exciting to be part of this. All right, so with that, let's transition from the high-level portion of the talk to some more of the technical details. And I'll try and walk through with as many pictures as possible, but really I'm going to try and show you some math so you can see that there's some statistical theory you can do underneath the covers. Just wait a couple slides until you want the math. Fred Sala is on the market now. I am not above advertising my postdocs. Fred's great. If you haven't already interviewed him, some of you have, great. If you haven't, you really should. He's amazing. I can tell you he's absolutely brilliant. Okay, end plug. All right, so what does our pipeline look like? Well, there's no hand-labeled training data anywhere. We have these 3 phases that we talked about. In the first phase, the user writes these labeling functions for related tasks. You could do multitask versions. There's all kinds of papers about this now. I'm going to focus on this second challenge here right now, which is once we have access to all that information, how do we understand those accuracies and those correlations that I was talking about? And I'll describe that at a high level first, and then we'll see the math. And actually, the math is not super complex. Okay. So the question's probably on your mind that I usually get asked at this phase of a talk. Well, how can you do anything without ground truth data? Let me show you. It's not that mysterious. So what we're going to do is we're going to think about this as the generative process. So the functions, if you like, every time a data value comes in, they can say yes, no, or I don't know. Okay. And you can make them do more complicated nonsense, but let's just stick to this because it makes our lives easier. So the functions come in on a particular piece of data, as we saw, and they vote person, person, hospital. And the way we model this is we say, oh, there's lambda 1 and lambda 2. They have some hidden accuracy. They're obviously correlated with y, which is the ground truth, but they're also correlated with each other. Whereas lambda 3, we're going to assume is independent. I'll talk about how to learn this graph later without training data, but for now, just imagine that it's given. So how do we learn the parameters and the strengths of these correlations without using any training data? Well, we're going to use the fact that because we see each one of these things vote many, many times on many different points, we can see intuitively how often they overlap, how often they disagree, and how often they agree. And if you're a statistician, that immediately suggests you form exactly one object, which is a covariance matrix. And that's what we're going to form. Okay? So here's how it works. So we're going to observe this matrix, okay, which is effectively a covariance matrix. I'm doing a little bit of sleight of hand, but just an affine sleight of hand, nothing wild. And this is creating here this nice covariance matrix. And the idea is that this green block we can actually observe. And the reason we can observe that is because we can observe how often lambda 1 and lambda 2 agree or disagree. So we can get an estimate when we multiply them together, okay? What we can't observe are the red pieces. And the reason we can't observe the red pieces is because that's their interaction with the ground truth, okay? And that ground truth is hidden from us, it's latent. So if we could estimate those things, we would be golden, right? That would allow us to back out the accuracies for this problem, and life would be really, really good. Okay. So we now need to do some manipulations on what we observe to the underlying parameters. And so what's going on here is that we have this inverse of the matrix, which we want, and we want to get the O parameters. We want to see that part that's underneath the covers. The problem is we don't have the full matrix sigma, so we can't invert it. But we can basically understand that it has fewer degrees of freedom in some cases. In particular, as long as there's enough independence in this graph in a way that we precisely characterize, it turns out that not only are there fewer degrees of freedom, but very precisely some of those entries we know to be zero, okay? And I'll show that in a second. The second observation we can make is that we can rewrite that matrix in terms, using the matrix inversion lemma, in terms of something that we see, which is this observed overlaps matrix, an invert, and this rank 1 parameterization, which is a rational function of the accuracies. But for us, all that matters is that when the expected value of zi is 1, that means it's perfectly accurate intuitively. And if it's random noise, it's exactly 0. Okay? And it's basically scaled accuracies in between there. The exact scaling comes from the matrix inversion lemma. Okay? All right, so far so good. Now we can solve this set of equations because that left-hand side is going to be 0 for a sufficient number of entries. In particular, anytime there's no edge in that graph, it turns out there's a 0 in the inverse covariance matrix. This is true for Gaussian graphical models, and it's also true under some technical conditions, even for discrete graphical models. It's a beautiful set of theorems that were known to stats human beings. Now, this looks like a low-rank kind of matrix completion-y style approach. But the problem is that sigma underneath the covers is full rank. So thinking about it as low rank is not really going to help you. Now, it doesn't matter so much if you're not a statistician, because you can just average up a whole ton of these things, and then you'll pay kind of proportional to the number of labeling functions. But you can do better. So the key idea is that even though it's high rank in a particularly interesting way. It's I plus UU transpose for some U, effectively. So it's identity plus low rank. And so this should have a very spiked kind of spectrum, and which should intuitively allow us to be able to recover it with dramatically fewer parameters. And indeed we can. We basically just solved that set of equations. I won't go through how. You can solve it in a variety of different ways. We have a couple papers on different ways to solve it. But a couple of things are worth noting. The first thing is that there's an obvious symmetry here. Z and minus Z are obviously symmetric solutions. If Z is a solution, so is minus Z. Just they only appear in pairs. And that makes sense intuitively. The reason is you can't tell the difference between everyone agreeing with the ground truth and everyone disagreeing with the ground truth at the same rate. So that symmetry really, really should be there. As I mentioned, if you had a random coin and you put that in as a labeling function, totally valid labeling function, it would have basically accuracy 0.5, right? It could be completely uncorrelated with what was going on underneath the covers. In that case, you have a 0, and notice that that's going to wipe out effectively an entire row and column of the matrix. And so you wouldn't expect to be able to recover parameters against that noise. Okay? And so, of course, what that means if you're a statistician is you scale as close as you have those accuracies to random noise. If your accuracies are really, really good, they're like close to 1, then life is good. You'll need few samples. As they get closer and closer to 0, you need more samples to distinguish noise from not. Okay? Now the last thing, and if you're a real technical nerd, I wanted to give you something to help you with your proofs. This is a technique that I absolutely love. It's due to Verschinen. So one of the problems with rank in general is that it's discrete. So you have, if you add in just a little bit of epsilon noise, all of a sudden you get something going from low rank to really high rank. It's not continuous in a way that you want to do your analysis. And there's this beautiful tool called effective rank, which basically is a smooth, continuous version of this. And this turns out to be exactly the right tool, as I'll describe, to handle all of these estimation problems. Okay? It's a simple quantity, by the way. It's just the trace of the matrix over the 2 norm, right? So the sum of the singular values over the maximum singular value. And it turns out that when we have separation, this gives us exactly the right scaling to be able to estimate this with nearly perfect quality. I'll return to this a little bit later, okay? So then we use this probabilistic training data, we feed it into some big nasty multitask model, and life is good. Informally, we can show that basically what happens is those labels are about as good as traditional ground truth labels. That is, they converge at the same rate. We actually can estimate that constant, and later I'll give you an even more updated constant. But there's one thing that you should worry about. So if you're a statistician, this looks like, oh, it scales like supervised data, which is great. But there's one thing that you should worry about. Traditionally, when we do learning theory, we believe that we have a random sampler from a population, that we can go underneath the covers and grab them at random. That's a dubious assumption in supervised learning. It's really tough to imagine that you would do that here. When you're passing data through functions, it's not clear that they will label in a kind of an IID manner. And so up to what you cover, this is a generalization guarantee, but you may have to do another random sample to make sure that you're not missing something. So that's a way of saying precision is fine, but you should really be suspicious of recall claims unless you independently validate them. And that comes out in the theory. All right, so I'll skip through this. There's a ton of work on this. This is just one random slide. It does actually work. It's dramatically better than majority vote. We've characterized the situations when it's better than majority vote. It's part of the reason folks are using it. It also protects you from things going catastrophically wrong, which is something really exciting. All right, so let me just go back to radiology. So this is that problem we mentioned before. We have text reports. We have images. The images are servable. These are not. Okay. So these folks basically spent person months. They labeled a bunch of data right here. That's their AUC curve. They then hand labeled person years, and they got another curve that looks exactly like this. There it is up there. Now, Jared went over to them and hung out for about 8 hours and said, okay, tell me about what's in those reports, just as I described. Let me write 20 or odd labeling functions that allow me to transfer information. Here's their results, okay? The days is because of running the deep models and the hyperparameter tuning. Now, the AUC is pretty close. Okay, great. Maybe we got lucky. What's really exciting is that this was something that was nearly interactive. This took days. Imagine the difference, and this is one of the reasons this has caught on in industry, that you can see how well your model may be performing using the weak supervision techniques, and then go back and spend the person years if you want to get a couple more points of quality. Now, what's happened over time is that people don't do that second step because they're iterating on their next feature. But still, it's a pretty exciting way of changing how people can construct these models. Okay. I should be clear, we maintain a blog about this. There's a huge amount of related work. I posted the slides. We've been maintaining these blogs about related work in the area. Please feel free to send them to them. We love to read your work. We love to have discussions about it. And it's kind of a really exciting community of folks who are working on this stuff, and it's growing. We've been throwing workshops. Very, very exciting area. I'm going to dive a little bit deeper into show you Fred's brilliance, and Paroma's brilliance too. She's also brilliant. But Fred and Paroma wrote this beautiful paper that was just an ICML, and I want to show you something kind of surprising, that you can even learn structure in this way. Okay? It's a little bit more technical. So one of the things we noticed as people started to use this is that they would build those labeling functions and they would use it like code. And this is what we wanted. We wanted them to take an old function and modify it and do new things on top. But the problem is they become very, very highly dependency, have a very high dependency structure. And if you ignore those dependencies, you lose about 4 or 5 points on applications that we cared about. This was in a recent Nature paper. So this is a pretty substantial margin that we're losing by ignoring those dependencies. And we'd like to be able to recover them. So how do you do it? So if you're a real machine learning nerd, this is learning dependencies in a new kind of structure. The key difference is that you have a latent variable underneath the covers. Okay? So just to give you some results here, one of our papers, a paper that appeared in a stats journal a little while later. Basically, the idea here is that you should get something that looks like d squared log m, where d is the sparsity of your underlying graph. And both of the results that were known previously had these exponentially worse dependence on m, which is the number of labeling functions. They were linear in m instead of being log m, which is what we would hope for from the supervised case. So you should hope that you have something that scales. If you have a really sparse graph underneath the covers, and it's not very correlated, you shouldn't need that many samples to recover it. But our previous approaches needed quite a bit. So that equation I showed you before actually gives you the insight in how to solve this. We just rearranged terms here. We have this observed piece, and we realize that we can model it as a function of a low rank plus a sparse term. Okay? And it turns out that this allows us, to basically use a technique called robust PCA, which was kind of pioneered in the 2010s simultaneously by Emmanuel Candez's group, who's now at Stanford, and Venkat and Alan Wilsky, who were at MIT at the time. And it turns out we need to modify their technique in a small but subtle way, but they looked at this really exciting problem and really nailed down the vast majority of them. Their sample complexities for our problem were just slightly off. And the approach to solve them is super easy, actually. I won't go and bore you with all the details, but I will tell you the punchline. The punchline is Vershinin is a genius, and he's amazing. And basically, the tool that you need to do is to redo their analysis with these tools that came out 2 years later and you actually get back to exactly the right sample complexity. Now, this is kind of miraculous because it says that you can learn the structure without having supervised data just as efficiently as the supervised case, meeting the lower bound. And it actually turns out that on some graphs, it's actually better sample complexity than was known in the standard supervised case. The old results had a d cubed in them, not a d squared. So it's pretty interesting that this area is starting to get at some pretty fundamental problems. So if you're a math nerd, highly recommend more of you come in and play in this area. This allowed us to get this revised estimate here of how many of weak supervision versus standard supervision. And this gets us down asymptotically to a factor of 2, which is exciting. It's really 2 plus epsilon. What that means is you need a number of samples. Basically, that's twice as many in the weak supervision setting compared to what you would get in the traditional supervised case. And you should get exactly the same scaling, which is interesting. And yes, of course, I'm talking about this because it actually helps the end model. I'll flip through this quickly. Some folks, some of whom are here giving talks later today, so I want to plug them. They did this great tutorial. They're somewhere up in the front. They're doing this thing on how Software 2.0 works for data integration and machine learning. They have a great website. They've gone and given a bunch of tutorials in various different places. Really exciting stuff that they've been up to over the last couple of years. I think it's important as people start to apply this to structured data, which is a really big challenge, especially for the systems and machine learning community, where so much data inside our large scale systems are structured, and people, I think, are starting to look at it, and it's a really exciting time. This also applies to things like self-driving cars and videos, in case you think it's just for text from the examples. And also another person who's on the market and is also great, Jason Fries. He's more of a bioengineering person, so maybe people in this room are not interviewing, but he's a really exciting person who used this for several years with both journalists who are doing these implant reports and also with the FDA, and had a bunch of really exciting impact about tracking down the fact that there are devices that were hurting people but weren't caught because they were only mentioned in the notes field, not in structured data for people to do analysis. A really exciting paper that I encourage you to read that appeared in one of the Nature partner journals. All right. So let me tell you a little bit about future directions here, where we're going. So this analogy to code irritates everyone, but I really like it. So I'm going to bother you with it for a couple more minutes. So if you think about traditional sort of supervision, it's really about like zeros and ones. It really looks like machine code. We're just putting the zeros and one in and trying to learn from them. What weak supervision was about, in the way that I told you in this talk, was basically when you have labeling functions that were directly coding, like assembly language, to produce, those bits that you were, previously banging into registers. Okay, so it's one level up in abstraction. But this gives us a whole hierarchy of things that we might expect and what we've been working on for the last couple of years. Using things like high-level languages so that you have primitives and abstractions, and you can actually do static analysis to get better statistical properties from them. We have things where we're trying to code an even higher level language. We have this paper called Babel Label and ACL where you spoke in natural language and we compiled it down to noisy labeling functions. And folks who were at a neuroscience company who couldn't write Python were able to write these kind of labeling functions. The potentially strangest, we had a paper about how you can generate these things from user behavior, watching people as they interact with machines, and treat that as a form of weak supervision, which is posted on our blog. Now, I don't run my group. My students and postdocs run my group. They're the real brains of the operation. And they decided that they wanted to write a blog post where they started to outline some of the directions that they found most compelling. That's a pretty good signal we're going to work on them, since they're the ones who actually do the work. And Dan and Laurel actually organized all of this. So please go ahead, send us feedback, send nasty things to me and nice things to them. One project in particular that's super cool is this flying squid thing. So this is if you want to nerd out with me during this conference. We got a logo, so it's official. That's how we do our projects. We get a logo and they're official. Look at that squid, it's in space, it's amazing. So that project is about how you do interactive machine learning without SGD, which may sound a little bit freaky. If you read the blog post and want to chat about it, it's the thing I'm particularly most geeked up about. And those smart humans at the bottom really did all the work. Okay, so the last little bit of thing I want to talk to you about in my last minute or two, a couple minutes, is this idea that when we introduce new abstractions, we have new problems, okay? And just this is not something that says like deep learning is bad or evil. I love deep learning, I use it every day. I'm a big user of it. But there are problems that you come in when you have these new abstractions. And if we don't look at it like software engineering kind of people or systems kind of people, bad things may happen. All the examples are from this paper that was written by these radiologists and Jared, which I advise you to check out. There was an ML4H and then a recently accepted paper that we posted soon. So my journey into this started with these eyes. So You know, if you could write a program that actually allowed you to do some machine learning task perfectly in Python, you should just write the Python code, right? You shouldn't use machine learning. That's a bad idea. Just write the Python code. If there's no specification out there anywhere in the world, right, then you should also not use machine learning. It's not going to discover your specification. Where machine learning works is in this intermediate step where we can't kind of coax out the Python program because it's kind of too expensive to write. And so the idea is what we want from machine learning systems is we want them to be able to pick out unintended signal. Okay? That's what we want. And deep models actually pick out more unintended signal underneath the covers. Okay? Now these eyes, what they have to do with is that people were actually looking at these eyes and trying to understand, you know, if they look at the iris, could they classify the gender? And it turned out underneath the covers that they would build their models and someone else would pick them up and they wouldn't generalize in any kind of meaningful way. And there was a great paper that explained what was going on. It basically said that what they were doing was we weren't finding gender at all. They were finding the mascara on the eyes, and that was how they were actually able to pick out gender with more than chance. Okay? And this really worried me because I started to think, you know, do we know how well these models are performing? You always have this kind of itch underneath the covers, like maybe they're picking out something bad or anti-causal here. What the heck is going on? Now, I used these slides actually in a keynote in ICML UAI when it was in Sydney. And people came up to me like, oh, those are jokers. Real machine learning people wouldn't make that problem. You know, no true Scotsman would ever do something like this. Like, not so fast, okay? So I'll come back to that in 1 second. Right? Now, if we go back here to this slide that I put up earlier, are we so sure that those differences are not anti-causal? And I'm gonna come back why there's reason to worry about what the gap actually is and where it's coming from. Okay? Now, as I mentioned, it's not just those eyes. These are things put out by very, very good groups. And I want to be extremely clear here. I would have made this mistake and 1,000 times worse. I'm not saying, oh, this is a bad thing. We don't have the tools to deal with these problems as a field. It's a huge pressing challenge in my view. So here's a model where we're looking at melanoma and trying to do skin cancer detection. Maybe you saw some of this work going on in the press. And you see there's the activation map underneath the cover for the CNN. It's looking at the lesion, it's pulling out some structures. It's mysterious what it's pulling out. Awesome. It's doing a good job. That's all we know. Here's another image that was actually in the test set, and it turns out that there were actually marks. Those marks indicate that you're going for surgery, as I understand it. And if you look at the heat map, it's not looking at the lesion at all. It's looking at the marks. Very concerning. Here's another example, pneumonia detection. This was actually in Jared's paper. So here are two images. These are of someone's lungs, and you're supposed to tell which one has pneumonia. I have no idea. I hate this kind of stuff. I hate those medical nonsense, right? It looks like two people. I don't know who's got pneumonia, and I don't want to know. You shouldn't trust me to look at this, okay? Now, it turns out that actually papers are published, superhuman performance, 87 AUC, people are really excited. These models are amazing. Well, there's a problem. No matter how many times they tell me, these labels could be permuted, I would have no idea. One of them has a drain and one of them doesn't. The problem is you only get a drain put in your body if you have pneumonia. So it's anti-causal. It happens after the diagnosis. Well, maybe it doesn't happen that much. Yikes. Turns out like 1/3 of the images have it in it. And in fact, when Jared went through and redid the analysis, turns out that the AUC drops from superhuman to, as Ben Recht in his pithy way on Twitter put it, worse than a first-year resident. Okay? And that's kind of an interesting thing that we should be worried about this. And these are smart human beings who are looking at this. I would 1,000 times make this mistake. I want statistical theory that makes me not make these kinds of errors. Okay? So we have been thinking about this. If you have ideas, come talk to me. We don't claim in any of this talk to have the right solution for any of these problems. But it's worth observing that classical models, that bag of visual features model, probably wouldn't make a mistake similar to this. You wouldn't write down a rule that says when there are purple dots, someone has cancer. You wouldn't write down a rule that says when there's a drain, then someone has pneumonia. Because you were involved in the mechanical construction of the model when you're writing the features. But now you're involved at a much, much higher level. And weak supervision is only making this worse. So we started to think about statistical theories. And so Jared characterized one kind of way that this happens, which he called hidden stratification. And he showed that basically there were these cases when people would have something called abnormal, and there would be many different pieces underneath the cover. So underneath pneumonia, there would be chest drain or no chest drain, would be sort of subclasses or strata. And we built a little bit of a theory that allows you to combat these cases and identify whether or not there's actually hidden stratification going on in your model. And one thing that I'll plug at the beginning, I said, you know, are we sure about how those deep nets are doing? Well, he's a smart dude. Those Cornell folks, they're smart. Turns out underneath the covers, deep nets very often, the dense nets in particular, actually do separate the space, and there are hidden strata that you can see when you actually peer in at the featureization. So there's some hope of automatically correcting for these errors, which is something that Jared found in his work. Super cool. Okay. So with that, in conclusion, I showed you kind of three things. I talked a little bit about Snorkel, which is this framework for rapidly creating training sets. It probably sounded crazy and like kind of weird, but for some reason people are using it. That's pretty awesome. We talked a little bit about these nuggets. I wanted to talk a little bit technically about how we do statistical estimation without ground truth, that you can build a theory that's inspired by some of this practice and do things in structural learning. And the last bit is that we are changing the way we program. This is maybe way too high level, but it seems to be true that like the way we spend our time and where engineers actually spend their time building things is radically changing. Making things run faster is awesome. I love those problems. I worked on those problems a lot when I started my tenure run. I feel like there's a lot of people working on that. There's a lot of stuff going on here about how we build these things, which really academics, I want to make a plea, should be looking at, because it really requires principles and rethinking some of our basic systems principles. Thanks so much for your time and attention.
Hi, I'm Mario from Apple. So if I understand correctly, you treat these features probabilistically because they are like programmed and you're not sure they're ground truth. What if you also treat ground truth in that way? Would that kind of improve?
Wonderful question. Yeah. So the idea is whether or not you treat ground truth as, again, as a labeler. And I would say that what you would think about there and ways that people actually use this is they say, well, not all ground truth was created equally. Some was created by a particular expert. Some was created by a crowd worker. Some was created by a contractor. Some was created by the developer themselves. And so you can model kind of the human expertise that went into creating that crowd worker. And that is actually something people do inside systems. So you're exactly right. You can get this refined notion. Now, whether or not it's going to be a huge bang for your buck, that's something at this stage, we kind of have to run and test it out. But that is something that people do. Wonderful, insightful question.
Lakshmi Ramaswamy from University of Georgia. Thanks for a very nice talk. My question is the Snorkel approach in general. How generalizable is it? In the sense that aren't there really, really subtle problems which may not be expressible in any sort of rules, but when I see it, immediately I can say whether it is this or that. Right. So, and isn't machine learning supposed to attack these sort of subtle problems? The promise of machine learning is really these sort of subtle problems, right?
So I would say two things. First, that the way that you say that this is what machine learning is supposed to attack, there I would probably pretty vehemently disagree, since most of the products I just told you were, machine learning products that are generating a ton of value scientifically and industrially and is somewhere where it's used. But there's a core of what you're asking that I think is really interesting, and I think is what the philosophical question that we're trying to get after here, which is at what level is that expertise that you're talking about that you can look at and there's a specification behind it, but you can't write down something for it. So clearly there's a gap. And the question is, how big or small is that gap? There's nothing that prevents you from actually looking at this kind of ground truth and deciding that after you run your Snorkel program, you want to layer in some more ground truth. But I would say even the way we imagine collecting that ground truth is pretty impoverished, and it's something we're doing in what we call observational supervision. In these examples, you imagine someone looks at an image and as you say, oh, I spotted it and I said yes. Well, actually, if you watch their eyes, this is something one of my graduate students is doing, you can understand the confidence. You can understand the regions of the image they looked at. And so one way you can think about what we're doing is modeling much more of that structure. So yes, there are cases where it's gotten very successful, where it has to deal with the rules that are underneath the covers. But really, as I tried to highlight on that primitive, what we're after is trying to formalize more of what's going on in that collection process. So if you imagine your person sitting out there and looking at it, we would love to be able to capture that. And maybe their eyes tell us, the radiologist's eyes say, oh, I'm really confident this is definitely cancer, or the radiologist had too much to drink, and so you shouldn't trust their labels, whatever the case may be. But we'd love to be able to capture more of that. So that's the philosophical approach we're going. But you're right, this is where we've gotten traction on some of these more concrete problems. Great question.
Very wonderful talk, and especially like the last part, you stress there's a lot of problems we need to rethink. Sure. And I have a particular problem on It says it's like suppose the human accuracy on AOC curve
Sure.
with 87 or so.
Sure.
Is it another dimension of the problem that a single number cannot represent the performance of a model?
Wonderful point, yeah. Yeah, it's a wonderful point. I mean, you're getting at this directly. So one of the things that's been really interesting to me, especially in industrial systems, is that we have, AUC and all those numbers. Not only do they not capture how well the system is performing, but they neglect some of the most important structure. So one of the things I think people, at least I kind of, when I started, after acquisition and went to industry for a little while, you don't care too much about that high level number. You care a lot about fine grained interaction. And so an AUC number, an F1 number will hide a lot of that interaction. Whereas on fine slices of the data, that's really where your quality matters. And actually, we published this paper in NeurIPS that was saying like, hey, this slicing idea is something that allows you to focus on those fine levels. But it all comes back to what you're asking. The frequency is a poor proxy for actually overall quality. Getting 90% accuracy doesn't matter if you miss all the cases that should have been operable, right? And honestly, recognizing a case where unfortunately the person's too far gone is also not helpful. There's a utility to these things that is poorly captured by these kind of metrics. That's a wonderful point. Thanks.
Hi, thanks for the talk. Alkis Poliziotis from Google. So as this becomes more popular, we're going to get an increasingly large corpus of labeling functions.
Yeah.
Any ideas on how to organize this corpus and how to promote its reuse so that not everybody has to rewrite a labeling function?
Yeah, wonderful question, Alkis. I think there's a couple of things that we're starting to see. So we wrote a couple of little thought experiments about this, and we've seen some places where people are starting to share their labeling functions. We saw people do things like using GitHub and actually forking them using existing code mechanisms. What we don't know is what are the unique things that you could build that would help you scale out and share these things in a scientific way. The Snorkel folks think about this a lot because what they're trying to do is apply these to various different industries. And when they see that they're applied to these various different industries, they want to be able to share across them. And so there are some things you can do there that are quite kind of clever to cut the time down even more. As you notice, we had this thing about dependencies. When we had those dependencies, that came because people were literally from one project saying, oh, I have all these things that label bone tumors. Now I'm looking at these others kind of related tumors. Let me just bash those against it and kind of modify. And that usage pattern is something that we're seeing quite a bit. And we hear from some of our friends at Google also about different ways that labeling functions are kind of cascaded together in certain applications. So really excited to study that problem. Thanks for highlighting it.